Great. So this is the talk on fast interference management, and it is my personal opinion. Next slide, please. So bottom line up front, I'm going to talk today about the concept of interference management speed. And this is a useful perspective to help think about some aspects of the future growth directions of spectrum management. Now, I'm drawing on an underlying definition of interference management, which comes from the Defense Spectrum Organization. The activities and processes executed to enhance electromagnetic compatibility and prevent, prepare for, respond to, and recover from electromagnetic interference. That is a beautiful, clear, and comprehensive definition. It's much better than anything I could find on the ITU website for what we're talking about here. So thank you to the DSO for that. So why is it important to focus on the speed of these interference management activities? Why is that fundamental? Let's go to the next slide, please. This whole investigation grows out of a thought experiment I did about a year ago. I was looking at some recent shared bands, the proceedings since about 2000, which we as a community sort of have an intuitive feel are somehow form a set. They have commonality with each other, but they're somehow different from everything that came before. So I asked myself, how could we most crisply identify the fundamental common characteristic of these rulings that differentiates them from previous regulations? Next slide, please. What I ended up with is the statement that in these rulings, the rights granted to new entrants depend on time-varying external information. External in this context means information that comes from outside the device or system that the rights apply to. So, for example, in TV white space, if you're a new entrant and you want to transmit, your transmission rights depend on the operational status of wireless microphones nearby. That's time-varying information. It's not available to you in the ruling itself. You have to collect it and process it to determine what your rights are. Similarly, in the context of CBRS, your transmission rights depend on the location of Navy ships with their active radars. So when we look at this hopefully crisp and useful description of this class of spectrum sharing, we notice this word time varying here. That's really fundamental. And when we're thinking about time, we have to ask ourselves, how fast does that external information change? That turns out to be a really useful categorization of different bands and different spectrum sharing mechanisms. So let's go to the next slide, please. So that's where we define the speed of interference prevention. We're going to define classes of interference prevention speed based on the rate of change of the external information that determines the rights of the new entrants. What I'm calling class 1 is more legacy, traditional spectrum management approaches. That's where the information that determines your rights is stable over long enough time, like say years, that decisions about what your rights are can be made entirely by the regulators in the rulings. In some cases, it might only be stable for weeks or months, but in that case, the regulators can't act on it, but it's still possible for human beings to manually collect the information, analyze it, and determine the rights. So the regulators might delegate those decisions to user organizations. So when you look at these rulings, you'll see things like exclusion zones for fixed incumbents that don't move over the course of years, or statistical models for propagation and deployment. Now, these recent bands that are of high interest to us, the spectrum sharing bands, this is cases where the rights for the new entrants depend on information that's only stable for minutes or days. That's what I'm calling class 2. So this would be, for example, the location and radar activity of ships. We see pretty substantial enhancements in spectrum access efficiency that we gain by going from class 1 to class 2, as witnessed that famous change in the exclusion chart in CBRS, where all of the coasts were excluded at first, and then they managed to shrink that quite substantially by building rules that depended on class 2 information. We can see that efficiency growth continuing in the future as we start moving from class 2 to what I call class 3. drawing on information that is stable only for milliseconds or maybe a few seconds. In this case, it becomes pretty hard to use a centralized system like a SAS, and we have to delegate the decision all the way down to the edge device. We can already see some emerging bands that require class 3 for efficiency. Just look at the experiments going on in the 3.1 gigahertz band out at Hill Air Force Base. You're trying to share spectrum between a radar on a fast-moving jet and a terrestrial cellular system. And if you try to make those decisions in a centralized nationwide SAS, you'd have to exclude a couple of states worth of cellular activity on the ground because that plane moves so fast and the radar's behavior changes. But if we delegate the decision to the edge devices and we can respond in milliseconds to seconds, we can open up a lot of new spectrum access. I anticipate that we're going to see class 3 in other bands in the future as well. So this is a useful perspective. When we're looking at a band, we're looking at a spectrum sharing case, let's ask what class the information stability time is in, and that gives us a lot of guidance for what we might be able to do in that band. But we can also look more broadly at what happens ex post. Next slide, please. So this is the speed of interference response. Now, in this context, it doesn't make sense to define this based on a time constant like seconds or milliseconds or minutes or days. We'll get there eventually. But the real fundamental thing that determines the different classes of interference response is the desired outcome for the potential victim of that interference. So this chart should be read from the bottom up. Start on the row that's labeled class 6. That's where we are today. That's where the time expected to respond to an interference event once it begins is so long that you really do expect the victim's mission to be significantly impacted. So if you have spectrum sharing, say, between a cellular system and a non-cellular actor, generally, if you get interference that's reducing data rates in one of the sectors, it can take days to weeks at minimum today to get that identified and mitigated. And that's a very significant concern for the mission of the cellular operators. Going forward, what we're really looking at doing is trying to move out of class 6 and accelerate into class 5. That would be a spectrum sharing system that's capable of responding to interference fast enough that it actually protects the success of the victim system's mission. An example for that would be a radio telescope. If you have an observation that you're going to try to do and there's some interference at that frequency, the radio telescope could switch to a different observation that's in its queue. And when it comes back half an hour or an hour later, if there's a high probability that that interference has been mitigated and gotten out of the band, well, then the radio telescope can still accomplish all of the observations it was planning to do that day. And we're now in class 5, where the victim's mission success has been protected. That difference from class 6 to class 5 is significant because it dramatically enhances the willingness of incumbent spectrum users to share spectrum. And that directly translates into accelerated proceedings and faster growth of spectrum sharing, faster growth of overall efficiency. So that's really important. I would note, though, that there's been little attention in recent regulations on using the spectrum sharing mechanisms to accelerate that enforcement. That's sort of an after-the-fact consideration. But as Mark Gibson told us on Monday, there's currently a bit of an impasse in the 6 gigahertz multi-stakeholder group about how those mechanisms should be used to accelerate enforcement. An acceleration, from say 2 weeks to 1 week probably won't make much difference. But if we can accelerate from class 6 to class 5, where we're really protecting the victim's mission success, that's when we get a qualitative jump in the success of spectrum sharing. Looking forwards a bit, it's a bit of science fiction, but the acceleration from class 5 to class 4 is where we go from an interference event that impacts the victim's mission, but is, we can still get to mission success. In class 4, the spectrum sharing system reacts quickly enough that you protect the victim's current activity. So an example of that, where you have a victim that is, say, a communication system, can we mitigate interference before the router queues overflow? Next slide, please. So that brings us to this overview icon, the 6 classes of interference management speed. This puts together all of the information I've talked about, the 3 classes of interference prevention and the 3 of interference response, and it shows the pairing of these into the 3 different time scales. 1 and 6 are the manual time scale, that's traditional spectrum management, and where we're really trying to get to is to the mission time scale and eventually to machine speed. Next slide, please. So this is what we call fast interference management. And that's really the goal of recent and we hope future spectrum sharing proceedings. Next slide, please. This view, I said, was useful for thinking about where we're going in spectrum management. So let me just point out some of the recommendations that come out of looking at things through this lens. First one here is that we shouldn't just focus on interference prevention speed. We should also consider interference response speed when specifying the requirements on sharing mechanisms. I will point out that if we're going to get into class 5 or class 4, we need automatic mechanisms. And those automatic mechanisms then are going to depend on setting quantitative protection thresholds that they can take action against. And that's been an ongoing debate, but I think we really are going to have to go in that direction. Second, if we're looking at continuous regulatory improvement, the theme of ISART, we shouldn't just look at potentially changing a propagation model over time or improving a power threshold. We should consider specifying that we may potentially accelerate interference management in a band through continuous improvement processes and try to incrementally get those efficiency gains that come from faster speeds. Finally, and I don't have really the time to fully explain the argument for this, the regulations in a band end up specifying the speed of interference prevention and the speed of interference response in that band. And once that's been specified and you develop those systems, it gets really, really hard to change that speed. But that speed ends up determining what missions can use the band and what types of systems you have to build to operate there. So given that we want to support a range of different missions and a range of different systems, we really should aim for a portfolio of bands which in regulation are specified to have different interference management speed. Next slide, please. This viewpoint of speed is not just about interference management. It actually turns out to be quite relevant when you look at the future of rights assignment, rights definition, rights trading, and so on. Again, not really the time to get into detail of this, but what I've found in my analysis is that if we're going to get to interference control down there at mission speed or machine speed, then as we start doing things like trading interference rights, one of those things that Martin Weiss did some really wonderful work on a decade ago, we need to think about doing rights trading at machine speed and mission speed as well. To have really a balanced system. That's going to be somewhat in the future, but as we are defining the rules and the mechanisms for upcoming bands, we really should be looking at accelerating the rights trading into these speed classes, not just the interference management. Next slide, please. So bottom line, I've tried to bring forward this concept that interference management speed is a fundamental attribute of spectrum sharing. And that makes it a useful perspective for thinking about our future directions in spectrum management. Next slide, please. So with my last minute or two, I'm going to talk here about something completely different. I'm going to really use the time to make a shameless plug to the ISART community. The program at NSF that I am the champion of, National Radio Dynamic Zones, or NERDS, we are anticipating soliciting proposals in 2023 for research that many of you, the types of areas that you have expertise in, research on the adoption of dynamic spectrum sharing from perspectives like social, behavioral, and economic research, how that interacts with technical regulatory changes, how spectrum user business models might need to change, how these new forms of spectrum sharing impact auctions and federal agency incentives. So I really want to solicit your attention to and potential proposals to this opportunity. We are anticipating these to be solicited as supplemental proposals to the study awards that we're issuing this fiscal year. So if you're interested in this, I encourage you sometime this summer, perhaps, to take a look at the slides and the video that are on the website. After the awards this year are announced, please take a look at the award search to identify and contact potential teammates. Participate in the first community open meeting. It'll be a virtual online meeting this December. And email us with any questions. We'd love to engage with you on questions, whether that's fast interference management or anything else that's related to the adoption of dynamic spectrum sharing. And with that, I will finish. Next slide, please. I do think we have a couple of minutes here for any questions. And I see one question. Whoops, it was there. Yes. How would you recommend handling interference response activities that cause an unnecessary disruption to the suspected source of interference when the actual cause of EMI is something else? In other words, what is the recourse for a shared user being disrupted or degraded because the incumbent user incorrectly attributes fault to the shared user when it was actually caused by something else? I mean, this is a super interesting question. One that I think is well deserving of research about how you set up the incentives and the mechanisms to deal with that. I would point out that this kind of an issue occurs anytime you have a shared resource, and it's difficult to identify who's consuming the resource in different ways. And we've got a lot of past history in other resource management activities that might be relevant to addressing that.